Hey, welcome back to the next episode in our series on aerodynamics. Today we're going to be talking about aircraft structure and specifically real-life aircraft structure, so full-sized aircraft and some of the structures that consist on them. So we're going to cover the 5 basic structures of an aircraft, which are fuselage, wings, empennage, or tail as it's commonly called, the landing gear, which you have to have on a full-size aircraft, and the power plant. And so first we're going to go over what an empennage is. So an empennage is essentially the tail of an aircraft. Typically, whenever you think of that, you think of the two control surfaces on there, which are the horizontal stabilizer and the vertical stabilizer. And you're all familiar with the traditional style of an empennage, where you have your vertical stabilizer and your horizontal stabilizer, and your body goes out from there, and you do whatever you want with it. This is the traditional style. It's very effective and it's used all over the place. However, there are many other different styles of empennages used in many different ways. So I've drawn out on the board here some of the common configurations that you'll see for empennages on an aircraft. Now, the reason you would choose one empennage or another relies on a variety of factors. Primarily, though, drag is the biggest factor when you're choosing an empennage. You'll see a lot of choices between a traditional or conventional style empennage and a V-tail empennage. And so the one will produce more stability and give you more control, but creates more drag. One produces less drag because you have less surfaces hitting the air, but like with the V-tail, you create more drag whenever you use your control surfaces, and there's a lot less stability associated with it. So as far as your basic empennages are concerned, you have your traditional style empennage, a T-tail empennage, and then a cruciform empennage is what this is called. And all that's modified here, of course, is the location of the horizontal stabilizer. And so the reason that we would want to modify the location of the horizontal stabilizer is so that it's left out of the oncoming air coming out of the wings or behind the fuselage, and it's left with more control. For instance, on the MD-80 aircraft, they chose a T-tail configuration. And this is because in their testing, as the aircraft tilted up, the turbulent air behind the wings went right through the horizontal stabilizer. And so if you were to be in a certain angle of attack configuration, you would not have any control in the horizontal axis. Therefore, they mounted this horizontal stabilizer on the top of the tail. Now this leaves you with a lot of room for wobble and instability, and a crucible is a mix between the two so that you can get your horizontal stabilizer where it is efficient and stable, but also out of the slipstream of your wings. We have other configurations as well, and these vary on stability. And so you have what's called an H-tail, a V-tail, and here's a twin tail. So why would you choose these over a traditional style empennage? With an H-tail, if you think about it, you have much greater stability in the horizontal axes and the yaw axis of your movement because you have 2 stabilizers instead of 1. And they're also spaced far apart, so this makes your aircraft much more stable. And so if you find with your traditional style aircraft that your analysis is not giving you enough stability, you have 2 options. You can either put another tail on it, or you can make your vertical stabilizer really, really big. And so for that reason, somebody might also choose a twin tail aircraft. You have greater stability with an H-tail because there's spacing, but that's also harder to manufacture. Somebody might also choose that with the twin tail. If you think about the F-15 Eagle, one hypothesis for why they might have chosen a twin tail would be they needed more horizontal stability, but to put a giant fin on it, a giant stabilizer on it, is going to be very, very visible to enemy aircraft or other systems. A V-tail is very interesting because it's actually a very efficient choice. Instead of having 3 surfaces in contact with the air, you have 2 surfaces in contact with the air, which greatly reduces your drag. However, as an effect, you have to have mixed controls. So if you want to yaw to the right, you have to pull up on one and down on the other, and it creates other moments and rotations in the aircraft that are not expected nor desired. However, you get greater efficiency from it. So in your situation, that might be a great decision. It also requires a lot more input as far as controls go, especially if you're working with autopilot systems. There are other more non-traditional types of configurations. I have 2 down here. There are many, many more if you want to research them. This is called a Y-tail. Has many of the benefits of a V-tail, but your vertical stabilizer down here gives you control in the yaw axis, but it's also a way to reduce drag. And also you have a twin boomed inverted Y-tail. And so why would you choose that? Well, if you have to have two booms for some reason, for the efficiency of your aircraft, or if you need it to be a pusher, it's the most efficient way to link up your control surfaces.
Now we're going to talk about different types of wing configurations. Primarily, most wings look essentially the same, but there are a bunch of different designs out there that each serve different purposes. The one that you're most familiar with is what we call a Hershey bar wing. And that's just a little nickname for it because it's just a straight rectangular wing. And that looks like a rectangle. And it'll make you fly, and it does a good job. One of the common early designs for getting a little bit more lift was to use a biplane, which is just two Hershey bar wings put on top of each other. And you'll see that a lot with World War I aircraft. So you got a biplane like that. When you ride on maybe airliner when you're going home for the holidays, or when you fly essentially anywhere on a common airliner, you're going to get a swept wing. And a swept wing is kind of like you took a normal wing that you're used to and bent both sides down so that it looks like this. And you know, the main fuselage of the airplane goes right here, and then maybe you have the tail back here. That is a really rough drawing, but this is a swept wing, and it serves its primary benefits as you get closer to the speed of sound, because there's some interesting flow phenomena that happen the faster you get, and swept wings help to reduce the drag at high speeds. Another common wing configuration that you'll see is kind of like a swept wing, but it's a delta wing. It's called a delta wing because it is in the shape of a triangle, and it looks like the Greek letter delta. This also provides a lot of good lift and stability at supersonic speeds. And so this is why the space shuttle has it. You'll see some fighter jets, they'll also have delta wings. Its main pitfalls are that you don't really get ailerons out of it, because you don't really have a spot to put ailerons, so you use elevons at the back. And we talked about that in a previous video on control surfaces. So you get a little bit less control over the airplane, but depending on the scenario, you might want to choose it over a different style. The last type of wing that we want to talk about is called a blended wing body, where you kind of take the fuselage, you take the wings, and you mush them together to make a flying wing. So it's just kind of like a big flat wing. And you can put cargo, you can put people on the inside of this enormous wing that flies. One big struggle with that is that you don't really have a tail, and so you have to do some smart controlling and maneuvering to make sure the airplane stays stable. But it is also a very efficient way to fly, and you'll see an example of this are some futuristic concepts that you can find online. In particular, you can see the B-2 bomber is a flying wing configuration. And each one of these different wing configurations are chosen because they're optimal for a specific purpose. There is not one particular type of wing that is superior to all. You focus on what you want your airplane to do, and then you can go choose the wing configuration based off of that.
As far as structural components are concerned in aircraft, wings and empennage cover the biggest sections of those things. There are a couple other structural components which we'll mention and talk about. In an aircraft which has a single engine in the front of an aircraft, such as a propeller or turboprop aircraft, the mounting area for the engine is called a firewall. And it's just a thick piece of material that can take all the forces and transmit all those forces into the aircraft so that it stays structurally sound. Additionally, in a larger aircraft, the main resource which an aircraft uses is, of course, its fuel. And you end up with lots of it for long flights. And so where is the best place to store that fuel? And in large aircraft systems, this fuel is actually stored in the wings. And this fuel actually ends up acting as a structural component for the wings. On takeoff, the wings are much heavier and much more rigid than they would be without fuel in them. And this allows for many vibrations to be dampened, and also to find a very nice, convenient place to store all the fuel. There's a lot of structural advantages to storing the fuel in the wings versus somewhere in the fuselage. Another primary component of the aircraft is the fuselage itself. Now, you have to ensure that your fuselage is going to be structurally sound and be able to stand up to the forces and rigors that landings, takeoffs, and pressurization are going to put on your aircraft. If you have a pressurized aircraft, the body of the aircraft will be kept at a pressure closer to ground level than it will actually be up in the air. And so you have an area of low pressure, and your fuselage will be considered an area of high pressure. And this causes forces to act outward on the body itself. In order to deal with these forces, often pressurized aircraft have to have extra reinforcement around the fuselage itself in order to handle those pressures. This is most commonly done in the form of aluminum ribs, which run along the aircraft's shell and all throughout the fuselage. And this allows the shell to be able to maintain the pressures of the aircraft. Now, depending on your situation, you may need these ribs to be thicker or less thick, depending on how much force you're expecting to take from the outside. And so, take for example, the 747 aircraft, which carried the Space Shuttle Endeavour for testing purposes for NASA. When you're placing a large, enormous force on the top of the aircraft, the general forces that the plane was built to handle are not equipped to take such a big weight on top of it. And so in order to accommodate that, engineers had to design a large bulkhead which goes across the top of the aircraft, which would be able to distribute the forces throughout the fuselage. There are other situations, such as around the area of the landing gear and wings, that also require extra reinforcement. And also, as you approach the empennage, you have to be aware of the torques that will be created by the extra weight on either end of the aircraft. These are all things that you have to be aware of when you're planning out the structures of your fuselage. So that's all we have on aircraft structures for today on real full-sized aircraft. Next, we're going to be talking about model and scale-size aircraft, and you'll learn about some of the systems that are used to take the forces of model flight, and also adding weight to those aircraft and seeing how they can withstand the forces which are required of them. And you might be called on to use that knowledge yourself someday, so we hope to see you next week.